the one that's numbered problem 41, but isn't really. But we're going to stick with that numbering because I don't want to change it and screw everything up. So the first one, which the original statement of the problem, which was to locate all the bound currents and use them to find the magnetic potential, the vector potential. And then from that, find the field. I have come to the conclusion that that's a difficult but doable problem, right? And there's a cheaty way to do it that's not so bad that I'll just mention to you. But first I'll mention what I decided to rephrase the problem to be. Locate all the bound currents, use them to find the magnetic field by one of three approaches. You choose your approach. One is to find the vector potential and take a curl. Two is do the Biot-Savart integral. Or three would be to use Ampere's law. I'm not going to tell you which of those to use. Okay? But I want you to basically take the bound current approach first to find your field. And then the second part of the problem is ascertain the correct field by finding H, which is really simple in this case, and then using H to find B.
Okay, so you first have to find it using, like, going directly.
Find the bound currents, and then use one of those three techniques. All right? Now the cheaty way to do this, all right, is which satisfies in spirit what I told you to do, which is that you can write, now I'm going to be missing factors of C in here, and 4 pi's, all right? Is that the vector potential is an integral over the volume, so I'll just make sure we remember that, of J of R prime over R minus R prime dV prime, okay, plus the integral over the closed surface of A of R prime R minus R prime dA prime, and let me just make sure that I've got the, aside from constants, right? But we know that A is equal to curl of B. So I just found the vector potential. All right. Once I know J and K, I found the vector potential. Now I take the curl of it.
Is it B curl A?
Yeah. All right. And if I do that, then you get around having to do some integrals that you thought you might have to do.
Is it B curl A?
What?
Yeah, that's B. B curl A. B.
Oh, sorry.
Wait, so how does that get you around the integral?
It takes away the infinities.
Yeah.
Because you're taking the derivative of it, and so it goes.
And it eliminates a lot of terms that you might actually have to integrate through because they don't contribute.
It ends up simplifying the expression substantially.
And that's the, I think it works, but I'm not going to do it for you here because I'll make a mistake. Right?
That's okay.
But that's an approach. I'm not necessarily recommending that approach.
How is that the cheaty approach, though?
What? Oh, because I said find the vector potential. And the way that you would read that phrasing on an exam is, I better find the vector potential. Not just write down the integral for the vector potential, but actually write it out in some final simplified form. I'm saying here, you can avoid writing it out in the final simplified form.
Is that a J sub F?
By not finding A, but just taking the curl of that.
And there's an easier one still.
So yeah, there are, yeah,
Two easy ones. So.
there are two really easy approaches to this problem.
So hypothetically, if we approach
One of which I told you not to use.
if we approached it this way, we would just have to write the answer in terms of the curl of those integrals.
Yes.
Okay.
And then solve for b.
And leave it in the form of
No,
those
then I
integrals?
probably would want you to simplify it because it turns out that there aren't that many terms to solve for. It's a lot of them are zero.
And leave it in the,
Solve for B and then hit A.
Or we don't need to
You
get
can do
a.
that, yeah.
Well, you said we don't need to get a at all.
Solve for A.
That's another cheating way to do it.
But you said we don't need to get a at all.
Yeah, but I do like Adam's approach, because I didn't say how to find A. I just said find A. And you could perhaps, like use Ampere's law to find B, and then find the A that satisfies that B.
That's a good idea.
I really like that, actually. You must have put some thought into it, or you're just used to us.
No, physics 2,
Yeah. Okay, does that, I think, probably, I hope, helps somewhat? Because if you find the bound currents, you come to the conclusion that they're pretty simple. Might be constant. Okay. Any other questions? Yeah.
So for that second one, you had shown us in class the dipole expansion.
Yeah.
Do we need to do that, or can we just solve the integral for m?
Solve the integral for m.
It seems really trivial. That's why I was really concerned.
Man, that dipole expansion took us.
If you think it was trivial, feel free to do a more difficult problem.
No, like, it just doesn't feel right. I
that big
think I may have done something wrong.
No,
We're only
that's
finding
how
out
you
from
find
the-
the dipole moment. Is,
probably
just
little
that
things.
yeah.
Really?
Yeah.
Oh,
I didn't solve it that way.
Okay.
I'm gonna do it the other way.
Physics, where everyone's complaining things are too easy. Yeah, I did.
By the way,
Yeah.
that expression you had earlier, that J, that was the free current, right?
There were no free
No,
currents.
there are no free
There are
currents.
none, right?
So they were just bound currents.
Why not just
But it's about current. Okay.
The answer in Ohanian for problem 11.14
It's
is wrong.
hilarious.
Yes.
Is it in
It's
the,
wrong.
is it in the errata?
He doesn't
No, it
know-
isn't in the
No, it
errata.
isn't. But he doesn't know how to read his own table.
Yes.
What?
His
His answer is hilarious.
He extrapolated the wrong way, let's say. He extrapolated right out from, he extrapolated, he didn't interpolate. He extrapolated outside the bounds
Of his extrapolation.
of where his answer should be.
It was quite funny.
That's what happens when you have very smart people doing arithmetic.
Well, I suppose also the reason why no one's ever caught it is because that problem's too easy for people to assign. From Ohanian.
Is that like an insult?
No.
It just means that most
I
people
could-
are usually teaching
I
right
can ramp it up if you want. I can.
Brian, shush.
You know what we need, actually? I think I might start this, is some sort of database where people vote on how hard the Ohanian problems are, and then you can assign the problems based on difficulty.
Oh, kind of like Rate My Professor, except Rate My Ohanian assignment.
Yeah, actually, I was thinking more like mastering, in mastering physics, the students vote on how hard the problems are, and then professors assign them based upon.
You mean by vote, they mean they get it all wrong?
No, students actually vote. The students actually can say this was a hard problem or this was an easy problem. And that information is given to me when I assign the problem.
That would be interesting.
Yeah. Okay, so Ohanian 1114, that's our problem 43. I don't think there should be any questions on that one. I'm not going to answer any questions on that. Other than to say, it's, if you work at it, it's 4 lines.
No.
Did you have to work to make it 4 lines?
Should be in the order of sports.
And problem 44 is a physics 2 question. Therefore, if you're having problems with it, go find a student in physics 2 and ask them how to solve
That's bold.
it. Yeah.
Could you go over just what your conceptual topic I suppose?
Actually,
You mean, wait, are you just like talking in general? Or,
still
because the
need
answer
that.
is,
No, I don't
no,
know the answer.
I can't just like think of a conceptual problem.
No, I have a specific question.
Okay, you may ask it, and I will either dismiss it as though it's too easy to think about, which means that I couldn't figure it out, or I'll address it.
Okay, I was wondering if I've been finding a lot in the literature about the vector potential field in mathematics, but for a little bit we played with the scalar potential field, and I was just wondering how that fits into, talking to Dave Hutchinson, and he showed me that triangle in Maxwell's, or in Griffiths,
Yeah.
that relates to like B, A, A.
Yeah.
And I was wondering where the scalar potential fits into. Because I was using it for current too. And
Oh.
I understand it.
Can I see the integral ID?
Oh.
Jake.
To be honest, I haven't thought about where it fits into that logic triangle. And I remember that I actually rewrote the triangle for myself, because I didn't like what he done, but I don't remember what I did. I just did it a week ago.
The
And we started it.
Which integral from
The scalar potential is actually almost,
You have that.
it's like if you notice that
Where
you've
did I
been given the appropriate boundary conditions, but you really do have to be given very simple boundary conditions.
One of these is,
Then you can use the scalar potential. And this solution is similar to the expansions. It is, just like the expansions that you learned about in the electric field potential.
So is that the scalar potential of A or the scalar potential of B? So,
It's the potential from which B would be determined by taking the gradient.
okay, so the grade.
You can't determine A
Okay.
from, directly
Okay.
from the scalar potential.
Okay, so taking the gradient of the scalar potential.
we know it.
Gives you, yeah.
Wait, Jacob goes to this.
And then you can uncurl
Yeah.
that to get A.
Okay, I just wasn't sure.
It's an anti-curl. Since we have antiderivatives, I think that we should have an anti-curl. Is there such a thing?
Yeah, there is a problem.
Is that what they call it?
I don't know.
Yeah, yeah.
But there's a problem.
I had an
This integral.
Yeah.
I do not know something about.
Okay, so hold on a second.
Oh,
I think we're done.
Okay.
Here.
Punch it. Silver button.
Is it this one?
That one.
Okay.